Lightweight concrete masonry and the benefits of quality assurance. During this presentation, I will address the following 4 learning objectives. You can expect to understand the influence of lightweight aggregates on concrete masonry performance by the use of illustrations and analysis. You will learn what building codes apply to concrete masonry products and how testing and standards assure quality. Number 3, you will increase your understanding of at least 2 tests used for compliance with ASTM C 90 specification for load-bearing concrete masonry units, as well as the purpose of absorption allowances for the 3 concrete density classifications. And number 4, by understanding manufactured lightweight aggregates, you will know how they make quality, structural-grade, lightweight concrete masonry possible. What is expanded shale? Expanded shale is made by expanding and vitrifying select raw shale in a gas-fired rotary kiln at temperatures around 2,000 degrees Fahrenheit. Similar lightweight aggregate can be manufactured using select clay deposits, resulting in expanded clay. For the rest of this presentation, we will use ES&C as an acronym for both expanded shale or clay, since the finished product is virtually identical in performance. The process produces a high-quality ceramic aggregate that is structurally strong, durable, low in density, environmentally inert, and insulative. It is non-toxic and absorbs water more slowly than other types of lightweight aggregate. Here pictured is an example of expanded shale as a clinker when it exits the kiln. The next step is to crush the clinker and screen the material to specified sizes for use in various market applications. Finer sizes are used in lightweight concrete block. Why should it matter to designers and specifiers what type of lightweight aggregate is used to make lightweight concrete block? Since aggregate occupies the most space or volume within concrete, its properties not only impact manufacturing challenges, but its qualities influence the performance of completed concrete masonry over the long term. Expanded shale is considered the gold standard for lightweight aggregate because of its contribution to the lightweight concrete mix design. It is the enabler that makes truly successful structural grade lightweight concrete masonry possible. We'll understand why as we go forward in the presentation. Let's briefly consider a typical manufacturing process. Starting from the mining operations, we observe raw feed entering the rotary kiln. As it passes and tumbles through the atmospheric zones within the kiln, the material is transformed into a pyroclastic flow at temperatures in excess of 2,000 degrees Fahrenheit. This process allows the material to expand. At this stage, the ES&C is referred to as clinker. It contains millions of tiny air spaces called pores. After exiting the kiln, the clinker is then cooled, crushed, and screened to size. Pictured here is a typical expanded shale facility located in Texas. The bottom photo clearly shows a rotary kiln expanding the raw shale. Steam is being released as the molten material is quenched and cooled. Any resulting emissions are cleaned prior to release to meet environmental requirements. Here we observed finished expanded shale lightweight aggregate waiting to be loaded into trucks or rail cars for delivery to various destinations. Before we move on to quality assurance issues involving lightweight masonry, let's spend a few moments understanding how lightweight aggregate performs in a concrete mix design. In the picture on the left, we view a magnified view of lightweight aggregate particles that are confined to a certain volume. While the different sizes of the particles seem to nest as they occupy space, they still leave interparticle voids. In this example, the voids between the particles are calculated to occupy 48% of the volume, as illustrated by the graph on the right. Within the individual aggregate particles themselves, there are many little empty pockets that resulted from the expanding process we previously discussed. These are called pores. Some of these pores are individual and discrete, while other pores may be connected to each other. In the above example, 24% of the volume is the pore network. What is left over, of course, is the strong ceramic matrix itself, which counts as 28% of the volume. It's important to remember the three components of the space occupied by ES and C. The first is the ceramic matrix. The second are pores held within that matrix. And lastly, the voids between the particles that will become filled with cement mortar. As we all know, it is the cement mortar that will act as the glue that will hold all the particles together as one. Similar to the previous slide, in the illustration on the left, we observe a similar looking distribution of heavy aggregate particles. That is, the voids between the particles is similar to the interparticle void of the lightweight aggregate. The striking difference is that heavy aggregates do not contain a pore network within each particle such as lightweight aggregates possess. It is useful to understand the difference and the similarities between heavy, that is, normal weight aggregates, and ES and C. In the graphic on the right, depicting lightweight aggregates, we have combined the ceramic matrix and the pore network in a graph structure. In this example, the combination occupies 52% of the volume, leaving 48% of the volume occupied by the interparticle voids. This interparticle void network is where the glue is distributed, holds these particles together. This glue is actually the cement mortar, which is comprised of water, Portland cement, and finer particles. Please consider for a moment the volume allocated to the cement mortar, and that it is similar when comparing normal weight concrete to lightweight concrete, assuming both samples being compared are of a similar size and gradation. The shrinkage of all concrete generally takes place within the interparticle void system, where the Portland cement mortar is used. That is why the potential for drying shrinkage within concrete exists within both classes of concrete. Since aggregate must be strong when considered for use in structural concrete, structural grade expanded shale is the ideal choice when structural grade load-bearing masonry is desired. We will explore this a little bit further in this presentation. The aggregate used to make structural grade lightweight block and masonry is the same quality of aggregate supplied to many other markets and industries that demand higher performance, even when not used as an aggregate in concrete. Here we see applications such as highway chip seal surface maintenance, requiring a surface that is resistant to wear. Other uses include use in lightweight roof tile. Applications also include horticulture and structural fill applications, as well as sport field technology, all requiring high resistance to wear and degradation. Additional information is available on various websites regarding many applications and uses of rotary kiln manufactured lightweight aggregate. A good resource is www.txiesc.com. Building codes provide for assurance of quality. During years of trial and error, empirical data was developed and used in these early codes. But these days, with the advent of computers, the engineered method of concrete masonry design is now the value-added method that gets the most from materials and workmanship. Whether taking the prescriptive or the performance-based approach, standards for selected materials required confirmation of quality by testing before and during construction. While not intended to be a comprehensive discussion of quality assurance programs, it is useful to see how lightweight masonry is treated in the code. Let's begin. Design and construction of masonry is now governed by the Building Code requirements for masonry structures, formerly ACI 530, and the specification for masonry structures, formerly ACI 530.1. In use, both the Building Code and the specification are sometimes referred to as the MSJC code. The International Building Code references this code, and so this code and specification becomes part of the IBC code. Since most, if not all, municipalities have adopted the International Building Code, they have also adopted the new TMS 402 code and the TMS 602 specification as shown in this slide. It is required by these model codes that they are both used in conjunction with each other. It is important to remember that the Building Code requirements for masonry structures and the specification for masonry structures are now referenced by the International Building Code and as such are part of the code. The code, the TMS 402, supplements the legally adopted Building Code and governs in matters pertaining primarily to structural design of masonry elements. It defines the minimum acceptable standards of design and construction practice. See Section 1.1.2. For example, this is where all the engineering formulas for allowable stress or strength designs are mandated. Think of the code as pre-construction requirements. The project drawing and other documents are based on this code. The specification is required by the code to control materials, labor, construction, and so on. Included are quality assurance requirements for materials, placing, bonding, and anchoring of masonry, grout placement, as well as reinforcement. The specification is meant to be part of the project documents and manual. Think of this as what is expected of the contractor during construction. The requirements can be written on project drawings as notes and in the project manual itself. These documents are the basis for the bidding of the project by the contractor. They are intended to be part of the contract as well. Here is an excerpt from the code commentary. Engineers have based their design on the minimum standards for materials and workmanship to ensure safety. Let's read through this quote together from the code commentary. A building code states only the minimum requirements necessary to provide for public health and safety. The building code is based on this principle. For any structure, the owner or the designer may require the quality of materials and construction to be higher than the minimum requirements that are necessary to protect the public as stated in this code. However, lower standards are not permitted. It is important to remember that the code only states minimum standards of quality. We can conclude that construction products or workmanship that do not meet minimum standards place the health, safety, and welfare of the public at risk. The code and the specification reference ASTM standards and test procedures for materials that are used. These also become part of the code. Standards and test procedures can be bought individually from ASTM. The National Concrete Masonry Association has compiled 39 plus standards most commonly referenced by this code in a handy reference booklet that can also be purchased. The National Concrete Masonry Association is an industry leader in providing technical assistance and education, marketing, and research and development to its members and to the industry. Visit ncma.org for more information. Let's review some of the ASTM standards relating to concrete masonry units as a concrete product. These are sometimes referred to as manufacturing standards, since block producers seek to ensure compliance with these standards. The primary standard used by block manufacturers is ASTM C, the standard specification for load-bearing concrete masonry units. There is also a standard ASTM C 129 specification for non-load-bearing concrete masonry units. The difference is that while both of these blocks look the same, individual load-bearing units must not have a net compressive strength of less than 1700 psi. Non-load-bearing units must not have a net compressive strength less than 500 psi. You can see how these units could easily be mixed up in a inventory or on a job site. So obviously it's going to require a great deal of care to be able to tell these individual units apart. The point here being is you certainly wouldn't want to mix or lay or install non-load-bearing concrete masonry units into a wall that is intended to be load-bearing. Also, it's worth noting that most block manufacturers do not inventory non-load-bearing concrete masonry units, as this would be a special request item. Check with your block manufacturer for availability of these types of units. ASTM C 90 refers to the use of normal weight concrete aggregates complying with ASTM C 33 and ASTM C 331 lightweight aggregates. Therefore, to consider the appropriateness of using these aggregates, the manufacturer will obtain test reports from their suppliers indicating whether or not the material being used complies with these requirements. When contemplating the use of any material, the manufacturer considers the impact on their finished product as well as the manufacturing process. However, the finished concrete product must meet all of the requirements specified in ASTM C 90. In this case, the block manufacturer would submit test reports on the concrete masonry units they intend to ship to a given project. In the case of ES&C, manufacturers can request test reports showing that expanded shale lightweight aggregate complies with all the requirements in ASTM 331. Within ASTM 331, there are three types of lightweight aggregates addressed, all types having to meet the same minimum requirements contained in the specification. The three types are generally grouped as manufactured, naturally extracted, and industrial byproducts. Expanded shale is a manufactured aggregate. This is a graph from the PCA Concrete Manual. From the left, this spectrum illustrates insulating concrete used for non-structural purposes, fill insulating concrete, and finally structured concrete. Notice that they are all called lightweight concrete. For example, a search of Dodge construction data using the term lightweight concrete usually returns a majority of specifications referring to insulating concrete. Expanded shale lightweight aggregate is generally not used to make low-strength insulating or fill lightweight concrete. It is recognized that expanded shale aggregate is an excellent choice when it comes to manufacturing structural lightweight concrete products. Some of the requirements in ASTM 331 include chemical composition, physical properties, and drying shrinkage. Note that drying shrinkage tests are based on a lab-prepared blend of Portland cement and lightweight aggregate using a prescribed ratio of 10 parts aggregate to 1 part volume of cement. 3 concrete bars are molded and tested for drying shrinkage potential. Bars cannot exceed 0.10% drying shrinkage. As discussed earlier, ASTM 331 presents minimum requirements. These requirements are not meant to imply that all aggregates perform equally. For example, some pumices may meet the minimum standards, but some may not due to the inherent variability of natural lightweight aggregates. Some may qualify as good lightweight aggregates for insulating fill or fill concretes, as previously demonstrated, but not perform adequately as a structural grade aggregate used in structural grade concrete. The same can be said of industrial byproducts when used as a lightweight aggregate. It is important to remember that compliance with ASTM 331 standard specification for lightweight aggregates for concrete masonry units is verified by test reports. The test report should report that the aggregate meets all of the requirements contained therein, including the potential for drying shrinkage. Reviewing ASTM C, the standard specification for concrete masonry units, we note that there are 3 concrete density classes for concrete used in block. These classes are normal weight, medium weight, and lightweight, each with their own concrete density requirements as shown in this slide. These are determined by using test method ASTM C 140, which defines the testing methods that are used to determine certain properties, except shrinkage of concrete block. All concrete masonry block, regardless of concrete density, must meet the same minimum concrete strengths and geometrical allowances. Higher strengths can be specified if required for design, but typically must be ordered well in advance of the date needed to ensure curing and strength attainment. A premium is usually charged for higher strength block. Check with the block supplier regarding additional cost relating to high strength block. Face shell and web thickness requirements are the same for all concrete density classes. In other words, lightweight block is not required to have thicker face shells or thicker webs to be load-bearing. ASTM C also includes requirements for drying shrinkage that apply to all concrete density classes. The standard refers to drying shrinkage in 2 places. Section 5.2 states that the linear drying shrinkage of units shall not exceed 0.065%. Then again in Section 8.3, where it states that linear drying shrinkage shall be based on tests of concrete masonry units. The standard refers to ASTM C 426 as the procedure for testing the potential drying shrinkage of concrete masonry units. Regarding shrinkage testing, Section 8.3 continues, made from the same materials, concrete mix design, manufacturing process, and curing method, conducted in accordance with test method 426, and not more than 24 months prior to delivery. Interestingly, the publication, Inspection and Testing of Concrete Masonry Construction by the National Concrete Masonry Association and the International Code Council states in its commentary on ASTM 426 that the test procedures are extremely sensitive to user error. Even minuscule deviations from the intended provisions of the standard or errors conducting the test can have a dramatic impact on the measured results. Therefore, only qualified laboratories should be used to perform this test. It is not required or even necessary to perform shrinkage tests on every geometric shape or size a block producer may manufacture, as long as curing methods, materials, mix design, and production methods have not changed. The standard only requires one ASTM C 426 test not older than 2 years from the previous test. Usually a set of 3 8/816 block are selected for testing as a representative sample of all the shapes and sizes using the same mix design as discussed. While the test may be more expensive to run than ASTM C 140, it is still required by ASTM C 90. And it only needs to be done once, about every 2 years. Materials, mix design, or curing methods cannot be changed unless a new shrinkage test is performed in order to assure minimum quality. We can conclude that in that case, Shrinkage testing would need to be performed more often. ASTM C requires that all density classes of concrete block meet the same physical requirements of required face shell and web thickness, strength, shrinkage, dimension tolerances. As discussed, AMC 140 and ASTM C 426 testing methods are used to determine compliance. ASTM C can be viewed as a manufacturing standard used by block producers to assure minimum compliance. Project submittals should always include test documentation from a qualified lab. Like other materials used in a project, a fundamental requirement for the administration and execution of assured quality programs are well-documented test results. Properly tested masonry products are important elements to assure that the masonry wall system will perform as designed. Absorption describes the amount of water concrete can hold when saturated and is expressed as pounds per cubic foot. ASTM C provides for 3 different absorption limitations for the 3 classes of concrete density. This is a laboratory test as determined by ASTM C 140. 3 sample units are oven dried and then subjected to total immersion in water for a period of 24 hours. Since masonry walls are never intentionally made subject to being totally immersed in water, what is the purpose or the intent of limiting absorption as stated in ASTM C 90? In past history, block manufacturers tested their normal weight block for water absorption to control the level of compaction of the concrete mix or the volume of interparticle voids. It was considered, and still is considered, that normal weight concrete should absorb no more than 13 pounds of water per cubic foot of concrete. This still holds true today. When block manufacturers started manufacturing lightweight block intended for load-bearing applications, it was apparent that the limit for absorbed water determined by the lab test would need, of course, to be increased. Why? Because lightweight aggregate is described in ASTM C31 that it itself absorbs water. So the control number for lightweight density block was increased by 5 pounds for absorbed water, making the limit 18 pounds of water for 1 cubic foot of lightweight concrete. This then served as an equalizer to determine the degree of compaction and interparticle void content for structural grade lightweight block. This slide is a magnification of ES&C lightweight concrete as used in a lightweight block. Since concrete used to manufacture block does not contain enough mixed water to make flowable concrete as used in ready-mix concrete, the mix is comparatively dry and moldable as used in today's block-making machines. Zero-slump block concrete of all densities contain voids unfilled by cement mortar, as well as a certain amount of unhydrated cement. That is why emphasis is placed on using a well-graded blend of aggregates to help reduce excessive interstitial voids. Additionally, good shrinkage controlling practices include thorough mixing of the batch, sufficient wetness of the mix, and sufficient compaction. All these manufacturing techniques help generate products not only just passing strength tests, but also improved impermeability for longer masonry service life. Many of these concerns are now addressed with the advent of modern, dynamic block-making equipment now in use in the block manufacturing industry. This graphic reminds us of the discussion we had earlier of the nature of lightweight aggregate particles and their ability to absorb water. ES&C is no exception, although it absorbs water more slowly than many other types of lightweight aggregates. This absorbed water is a benefit that provides curing internally. The graphic in the slide compares a lightweight particle to a normal weight particle. The top half of the graphic depicts what is going on while the concrete is fresh, and while the bottom half relates to hardened concrete. During the wet batch mixing and then molding of the lightweight block, a certain percentage of the mixed water is absorbed at the surface of the lightweight aggregate. This seeks to combine with any water already present deep within the particles. Empty pores serve as reservoirs for the absorbed water. In the hardened state, the water in the aggregate particles serves to improve internal curing. The transition zone, the area around the lightweight particle, remains at a low water-cement ratio, therefore improving the bond strength on the irregular contact zone. Absorbed water within the lightweight aggregate improves the strength and impermeability of the concrete and has nothing to do with drying shrinkage potential. Just because lightweight block absorb more water, as we just discussed, does not mean they are more prone to shrinkage problems. It is important to understand that the water stored within the lightweight aggregate does not affect volume or expansion of the concrete or contribute to drying shrinkage. It actually counteracts cement's shrinkage characteristics by improving strength through internal curing. Test reports show that properly manufactured lightweight block using expanded shale lightweight aggregate and good manufacturing methods yield high-performing lightweight concrete masonry units, resulting in quality lightweight masonry walls. Lightweight block made with expanded clay or shale lightweight aggregate, produced by the rotary kiln method, provides strength while not creating a need for more cement. The particles are manufactured to consistent performance standards that result in lightweight block exhibiting considerably less shrinkage than lightweight block made from many other types of lightweight aggregate. Performance has been proven time and again in the testing laboratory in over 50 years of concrete block production. As an example, here are the results using ASTM C for lightweight blocks recently manufactured in a Texas block plant. Key numbers contained in this report are net compressive strength of 2,790 psi. The block had a dry density of concrete of 99.3 pounds per cubic foot, clearly under the 105 pounds per cubic foot limit for lightweight block as described in ASTM C. The total absorbed water is 13.4 pounds per cubic foot, well under the 18-pound limit. The dry weight of the block is 26.6 pounds, about 27 pounds. The real question is, how did this block perform as far as drying shrinkage? Did it exceed the required limit established in ASTM C of 0.065%? As we discussed, ASTM C also requires shrinkage testing according to ASTM C 426. Here is the test report for the same batch of block we tested in the previous slide. As shown in the graph in this slide, the block leveled out to an equilibrium shrinkage of 0.044%, well under the manufacturing limit. But what is the F'(m) of this same block? F'(m) being an indication of the concrete masonry meeting the expected masonry strength for design. For this, we test prisms. ASTM C 1314 is used to construct prisms to confirm the F'(m) of masonry. The lab used the same block to construct prisms, and the test showed an F'(m) of 2,780 psi, just 10 psi less than the unit strength. We used Type S mortar in the construction of prisms. Prisms can be pre-tested by the block supplier and the report can become part of the submittal package. Or, prisms can be tested during construction to provide quality control checks as outlined in ASTM C 140. Regarding the issue of shrinkage in lightweight block, we received a response from the author of an article on lightweight aggregates and block, which appeared in a 2002 Masonry Chronicles newsletter, which was intended for the California market. We provide here an excerpt from the letter. Quote, "Units, lightweight, that are correctly manufactured and cured and satisfy the intent of the building code in ASTM C 90, which contains specific shrinkage requirements for concrete masonry units, will perform well if correct construction practices are adhered to. In our experience, concrete masonry units constructed with lightweight aggregate have performed excellently from a shrinkage perspective, and we see no reason to disallow their use." To understand shrinkage potential in masonry, we provide an example of a crack control coefficient that is based on guidelines from NCMA's Tech 10-3. There are three main types of shrinkage in concrete: thermal, carbonation, and drying shrinkage. Here we want to know how much length change, in actual inches, should be designed for in a 50-foot long wall. Our example shows that the potential thermal movement is 0.19 inches in a 50-foot wall. The potential shrinkage from carbonation is 0.15 inches in a 50-foot wall, and the potential drying shrinkage is 0.13 inches in a 50-foot wall. Add these together for a crack control coefficient of 0.47 inches in a 50-foot wall. As can be seen, drying shrinkage is the least issue to consider when considering shrinkage movement. The issue of drying shrinkage is addressed by standard ASTM C 90, which limits drying shrinkage to less than 0.065%, as established by testing per ASTM 426, as we have previously demonstrated in previous slides. So good manufacturing practices include not only curing in a curing chamber, but including a period of time in which units are allowed to air dry at the block plant. After delivery, the block producer is no longer responsible for units being too wet to install in the wall. It then becomes the contractor's responsibility to make sure blocks that are too wet are not installed. The installation of excessively wet block in fresh masonry may experience excessive drying shrinkage. Consider that the first step in the design of engineered masonry is the determination of anticipated service loads. Once these loads are established, the required strength of masonry can be determined. This is represented as F'(M), the specified strength of masonry. The specifier selects one of the following methods: the unit strength method or the prism test method. The unit strength method is the least expensive. Therefore, the most conservative value for F'(M) is used. The designer considers the strength of the concrete masonry unit as well as the mortar type to arrive at a masonry strength. Sometimes unit strength may not be verified, so conservative values are used to assure quality of masonry. This may not be the most cost-effective method for the project, since very often more reinforcement or materials may be needed. Here we see how the unit strength method is applied to determine the compressive strength of masonry for design purposes. Note that prisms are not constructed or tested. The code says that block meeting the minimum requirements of 1900 psi net compressive strength as provided in ASTM C 90 will provide a design strength of at least 1,500 psi as shown in the above chart. Also, block strengths between 2,800 to 3,050, depending on the mortar type used, will provide a 2,000 psi design strength, and so on. How does an engineer or designer know what the block strength is, and if it is in compliance with ASTM C 90 or the strength specifications? Initially, it is confirmed by a test report provided to the contractor by the block manufacturer before the job is started. To increase our awareness of quality assurance, consider the following. Owners can expect block to be tested for compressive strength, absorption, density, and moisture content to prevent drying shrinkage. Moisture content is controlled at the job site by the contractor. How often should block be tested during construction? ASTM C 140 Section 5.2 contains requirements for testing block during construction for quality assurance. These are just minimum requirements. More tests can be directed by the purchaser according to ASTM C 140. This is all part of the quality assurance and control requirements provided for in the code and specifications. Here is an example using the unit strength method when calculating F'M using the tested block we presented earlier. As you recall, that block had a net compressive strength of 2,790 psi. By using interpolation of the unit strength table, we see the engineer must design the masonry using just 1,994 F'M, or at the very least, the design does meet the 1,500 psi F'M typically needed for structural purposes. In this example, is the value of higher strength masonry appreciated or quantified? Let's consider the alternative prism strength method. Let's consider briefly option 2, the prism test method. Using the same block we previously showed by test, that the lightweight block actually yielded more strength performance. The prisms made from lightweight block that tested 2,790 psi net compressive strength actually tested 2,780 psi prism strength, almost equal. This shows that actual in-wall performance is much higher than that provided for in the design based on the unit strength method when using lightweight block using expanded shale lightweight aggregate. Pre-testing by the prism strength method can provide design information that can be used for more sustainable masonry. And at the very least, test reports shown here do reveal more value than using the unit strength method. Consider just a few of the benefits of assured quality as applied to masonry walls. It means longer service life and lower maintenance costs for building owners at virtually no extra cost. Designers could use less reinforcement and materials based on real masonry strengths. Although not necessarily needed for structural purposes, architects and engineers should consider that higher strength masonry provides real performance benefits. To name a few, water permeation from wind-driven rain, acid attack, and aesthetic deterioration such as paint loss are greatly diminished with quality lightweight masonry walls made with lightweight block using expanded shale or clay lightweight aggregate. A brochure entitled Top 10 Sustainable Virtues of Quality Lightweight Concrete Block Masonry is available. Contact TXI for a copy of this brochure. Lightweight block masonry containing structural grade expanded shale or clay is the right choice for structural masonry. Consider its proven track record, its high thermal performance, fast installation, lower dead loads, reduced reinforcement, thermally stable, its noise absorption, its contribution to sustainability. It provides for long life cycle performance, and many other reasons too numerous to mention during this presentation. References. The end, and thank you for your time.